Okay? You can actually solve this problem either with method of section or method of joints pretty quickly, right? Are there any zero force members in this? BC, right? That guy's 0. Okay? So then I'm looking for the load in member DC, this guy right here. So method of section says I could slice it right there and I end up with only 3. Or I could do method of joints here, which would tell me then the load in BD and in AC. And so then I could move down to joint C and solve it kind of in 2 steps that way. So let's do it both. Let's do method of sections first. Okay. So method of sections. It's going to look like this. TBD, TCD, and TCE, and 130 pounds, right? So some of the forces in the X needs to be 0. I'm going to say to the right is positive. So I'll have TCE. Let's see, these are 3, 4, 5. So plus 3/5 TCD plus TBD minus 130 times 5/13 equals 0. I can do the sum of the forces in the Y. So it looks like I just have 4/5 TCD minus 12/13 times 130 equals 0. And I can stop right here, can't I? Because 13 and this cancel, I end up with 120. So 4/5 TCD equals 120. Or TCD 80% of, well, no, 120 times 5. Ouch, 600 divided by 4, 150. Okay, and that's in tension. Okay, so TCD is 150, that's the answer. If I did this method of joints, right, I'd have to start at A. And I'd say that there's 130 in that direction, TAC, TAB, and I could say that TAC, I'll sum the forces in the Y, I guess I'll show you what I'm doing, is equal to 0. So negative TAC times, what would that be, 4/5 minus 12/13 130 equals 0. So we could solve that right off and find that TAC 120. So we're back to that TAC is 150 pounds, right? What? Am I right? Okay. But all right. So now I'm going to go down to joint C. And if I can identify that this is a zero force member, then I know that I have TAC of 150 pounds. And let's see, that would be in compression, actually. So that means that I'm going like this with 150 pounds. And then I have TCD and TCE. So now I can say, oh, well, let's sum the forces in the Y direction. Set that equal to 0. Up is positive. Looks like I have negative 4/5 times 150 plus 4/5 TCD equals 0. And we see right off that TCD then is 150 pounds, and it's in tension. Either way works. All right. Go ahead and give yourself some points out of 10 and pass it in. Sir? All right, so as promised, we're finishing chapter 6 today. It's kind of a big, chunky section. This is section 6.6, and it's called Frames and Machines. Okay. And the idea of frames and machines is they involve multi-force members. And they're typically pin connected. So if I have a pin, what types of reaction forces do I have at the pin? Yeah, maybe I'll have some AY and some AX. Okay. And the trick with these is that if they're multi-force members, they're often not solvable until we separate them into pieces. Okay? So the classic example is a pair of pliers. It's a simple machine. So here I have a bolt or a rod, and then I've got these pliers. Right? Not the most beautiful pliers in the world, but you get the idea. There's a pin that connects them right here. And maybe we apply some force. Let's say we apply a force of, I don't know, 30 pounds. Okay. And that's going to cause some smashing, right? So we're going to say that on our bolt here, the bolt pushes back on these with some unknown force P, right? Okay. But then at the pin that holds these together, I have some reactions. We'll call that AY and AX, right? And I might be interested to know what the load P is and AY and AX are. Okay? Or what the load on the pin is. Now, the problem is, let me give you some dimensions here. Maybe we'll say that there's 6 inches from the pivot to where I'm applying my 30 pounds, and that there's 1.5 inches from the pivot to where the bolt's being chomped on. Okay. So we can solve this a couple different ways, but first we need to draw free body diagrams, because really what's going on, technically we don't know that these P's are the same. So I should probably have them as different variables. So let's call, I'll put a point here that I'm going to call B and a point here that I'm going to call C. And so maybe I'll call this the P at B and P at C, right? So it looks like I have 1, 2, 3, 4 unknowns. And that's more than I can solve with my little equation. So I'm just putting a point at the top and the bottom of the bolt. And I'm saying that there's some squeezy force there, okay? Now we can't really solve this, but there's a trick with frames and machines. We can take these apart, okay? So if I take the two pieces of the pliers apart, I'll draw two free body diagrams. I'll start with the top one. Okay. And if I do this, my free body diagram says I have some piece of B. I have 30 pounds. Right? And I have some AY, AX. Yeah. The reactions at the pin and at the jaws. Okay. Yeah, so the question was, what are we trying to find? And the answer is the reactions at the pin and at the jaws. Okay. So let's see what we can do here. We could say that the sum of the forces in the x is equal to 0, right? Say to the right is positive, so it looks like we just have AX equals 0. Okay, that's one of our unknowns. How about if we sum the forces in the y direction and set that equal to 0? Looks like we'll have PB plus AY plus 30 equals 0. Right? And we can sum our moments. Where would you like to sum your moments about? A sounds good to me, right? It eliminates a couple things. Counterclockwise is positive. Hey, in grading your homework, I noticed people are still, at least at the time of the homework, which I realized was a week ago, we're really struggling with the signs on moments. Okay, so people were losing points on homework because they had the equations right, but just their signs for the moments was incorrect. So make sure that when you say the sum of the moments about A and counterclockwise is positive, that means if I hold the whatever it is at point A and then I push in the direction of the force, that tells me if the paper, turns counterclockwise, that's positive, and if it turns clockwise, that's negative, right? So if I sum my moments at A here, oh, what do we have? We've got plus 30 times 6 minus PB times 1.5 equals 0. Okay, so we can solve this and find that PB is going to be 4 times that, so 120. Okay. So we couldn't solve this before because we had 1, 2, 3, 4 unknowns. But when we break it into pieces, we can. Now there's going to be some cases where we'll actually have to draw both halves of the pliers in order to solve it. And in that case, let me draw the other half. Right. When I draw my free body diagram of the second half, I need to be careful when I come to AX and AY, because what happens is if I draw AX and AY being in the positive direction for the first body, like I've done here, right? AX and AY are positive for this guy. They will have equal and opposite reactions on this. Anytime you split it, if you have unknowns at those locations, they need to be equal and opposite.
But if it's just a force like 30 pounds, then
if it's only reacting on one side, not the other, you don't have it.
So here the 30 pounds is on this handle, so it stays there. PC, same direction as I had it in the big one, but when I've just drawn one variable, there's actually two things going on there, right? Because there's a pin here that acts on both of these. And so if on the first one I say that it's going in the positive x and y, that means on the second one it has to be in the negative x and y, because they're equal and opposite. Right? Because if you think about it, if this is the pin, right, and plier 1 is pushing it on it this way, but we know that it's in static equilibrium, right? So if arm 1 is pushing it that way, then that means that the other guy has to be pushing it the other way or the pin's accelerating, right? Okay. All right, so this is kind of frames and machines in a nutshell. Is anytime you have a 3/4 member, what you need to do is take it apart at the pins, likely, and then where the pins interact with each other, you just make sure that you get the directions of the unknowns in the opposite directions, and you can solve for the unknowns. Okay, so let's do some examples, because this is all kind of hypothetical until we actually do it, right? So let's start with, this is a frame, okay? Yeah, so a frame just supports something and a machine kind of transfers load. So a machine takes a force in one direction and applies it in another direction or multiplies it somehow. So like pliers are a simple machine because they're taking the squeezing force you're giving of, like in that example, 30 pounds, and they're turning it into a squeezing force of 150. So it's a simple machine, okay? Whereas a frame is something like what we have here. It's just designed to hold a load. Okay? It is a funny looking frame. All right, so get this in your notes. Yeah, so machines can translate the forces, meaning like maybe they turn a vertical force into a horizontal force or something like that. Yeah.
What are we trying to find?
Right now you're just putting this in your notes. So hopefully you get a free body diagram that looks something like this. Okay. And we're asked to find the vertical and horizontal reactions at pin C. Okay, so if I left this all together, let's draw the free body diagram of the whole enchilada. Okay, so we have CY, we have CX. What else do we have? No, that's it. That's inside it. So we'll have AY and AX, right? How many unknowns? A and B is a two-force member.
Aren't A, B, and B, C being held together by a pin?
They are. Yeah, so the question is, aren't A, B, and B, C being held together by a pin? And the answer is indeed yes, they are. That would be an internal reaction instead of an external, right? So at C and A, this is where the frame is being held up. You're right that there is a pin at B, and so yes, there are some BX, BY forces going on there, okay? Now, we can't solve this right off the bat unless Liana points out, hey, isn't AB a two-force member? And it sure is, okay? So it's still a frame, though, because we can't, we have to take it apart to solve it. Yep, Liana?
How do you recognize whether it's internal or external?
Okay, so the question is, how do you determine if it's an internal or an external pin? And the answer is, I guess, if it's at the ends, you know, or if it's connecting two links, which we don't know the values of, it's internal. Okay. So having this, we do know something by identifying that this is a two-force member, right? What do we know? We know the direction of its reaction at B, right? So I can actually just say, oh, let's draw my free body diagram of member BC, right? How do we know that it's a two-force member? Joseph has got it, that there's no loads, and there's 2 points where force is applied, right? Okay. And so my free body diagram is going to look something like this. But the trick is I know the direction of FAB, right? So now with these 3 unknowns, I can solve this. I had to take it apart, though, in order to be able to solve.
You don't have to add A, Y, and AX?
So I could add AY and AX, but I'm looking at member BC, right? But I could have BY and BX, except for the fact that I identified astutely that this is a two-force member. So therefore, I know the direction. Okay. So I'm going to pause it. I want you to go ahead and solve this. I'll solve it and we'll compare notes, okay? Okay. Hopefully you got something that looks about like this. Yeah, this should actually technically be 467. It's getting sloppy with my rounding rules. Okay. You got what?
On CY, I got 466.4.
Yeah, I think it should be 466.6. Okay. So let's try some of these that are a little bit more prickly. All right. Let's look for a nice prickly one. It's an engine hoist, so of course I like it. Okay. The hoist supports the 125 kilogram engine. Determine the force the load creates in member DB. All right, so member DB, this guy right here. Oh yeah. Mm-hmm. Why is the fan so big? Because your engine actually has lots of little explosions in it that happen every second that make heat. Any other questions? Okay. Why doesn't it have a radiator? Because you don't take the engine out with the radiator. You usually take the radiator out and then take the engine out. This is what an engine looks like when it comes out. Okay. All right, so are there any two-force members here? Yeah, DB is definitely one, so the value we're looking for is a two-force member. FB, also a two-force member, right? Hydraulic ram. Okay. So is this a frame or a machine? Yeah, it is. Okay. Because is member GE a two-force member? Nope, because force at G, force at E, and force at F. Right? How about member EDC? Two-force member? Nope. Force at E, force at D, force at C. How about CBA? Nope, because there's force at A, force at B, and force at C. Yeah, yep. If there's three force members, it's likely we're going to have to take it apart to figure out how it works. And it's a machine, yep. All right, so go ahead and draw this. It'll take you a minute. You don't have to draw the fan on the motor if you don't want to, Brendan. You can just not. Yeah, draw a circle. Draw a flux capacitor. my free body diagram looks like this. Got to be careful. They're trying to trick you by saying that the engine has a mass of 125 kilograms. So remember, we have to multiply that times 9.81 to get the actual force. They are tricky, tricky. So that's 1,226 newtons. Okay. So where are reactions on this guy? Where were the wheels? Yeah. So there's AY and AC. So if we say that this thing does it give us the weight? It doesn't. So we can just look at this and determine what our reactions are, right? How much of the load is carried by AC? Where's this force located compared to AY? Right on top of it, right? So if I sum the moments about AY, what causes a moment about AY? AC. Anything else? No, I'm not looking internal right now. I'm just looking at the reactions, the external reactions. AY, oops, this should be CY, not AC. CY, okay? So let's sum the moments. I want to sum the moments about A. They need to be equal to 0, okay? So what causes a moment about A? CY, what's the lever arm? Anything else? What does CY have to be equal to? 0. Right? This thing is on the verge of tipping if it has no mass. If I move the engine just a little bit this way, it's all going to crash over. Right? Okay? That's not what we're concerned about, though. We're looking for, in this guy right here, we're looking for the force in that. Okay? Where do you guys want to start? How can we go about finding the load in BD? Okay, so we could find it from member AC. Knowing that FB and BD are two force members. All right, I like that. Okay. Yeah, I like that. So Liana says, and so what we're going to have to do is look at member ABC on its own, right? So let's draw our free body diagram. So we're looking at this. We're looking for member BD, but we notice that, hey, FB and BD are two force members. Everything else is a three force member. The only members that we know anything about are GFE and ABC. So ABC interacts with BD. So let's try at ABC figuring out what we have. Okay, so if I draw ABC, I'm going to have 1226 going up. At C, I'm going to have the reactions between, because there's a pin at C that goes EDC to ABC. So I'm going to have some CY and CX. Now this is a different CY than the reaction, right? This is due to the pin that's hanging out there, right? Because even though the wheel isn't pushing up on it. There's still this pin joint, if we go back and look at it, right? So if we look here, these two guys are pin connected at C. So that pin has a vertical and a horizontal component possibly. Then we have at B, we'll have FBD and FFB, right? How many unknowns? Too many, right? Does everyone feel comfortable with the fact that we have too many unknowns here? Okay. Let's go to the other 3/4 member where we know something. That's the top, GFE. I'm going to label this so that we don't get confused. This is A, B, and C. Let's do GFE now. G, F, and E. F, we know the direction of. I've already run into problems, though. Can I draw FFB this direction? Why can't I draw it in this direction? It is a 2/4 member. Why does it go the other way, Brandon? Because it's an equal and opposite reaction, and in ABC, I've drawn it going up and to the left. So that means when I draw it at the other end, I need to have it going down and to the right. Okay? These guys need to be equal and opposite. If I had them both going up, the whole thing would be accelerating up, right? Okay, so I have to make sure that because I drew this one first, and I made the mistake of saying that FFB was in tension, if we look at it, is FFB going to be in tension? It's not, right? It's in compression because this thing's pulling down, and so it's trying to smash FFB. But I didn't see that when I drew it, and that's just fine. I drew it this way. I have to stick with that and say, okay, then when I draw FFB again, it has to be going in the opposite direction. All right? Okay. Let's see, what else happens here? I'm going to do my EY and EX. How come I can't just say that E is in the vertical direction here? No, because this is a different joint. So the idea was it's the opposite of CY. That's not true. That's not why. I guess what I'm asking is how come I have to draw both the horizontal and vertical? How come I can't just say, well, there's this member right here, EDC, so the only thing it can do is go straight up? Is that even true? Why is that not? You're shaking your head. Why isn't that true? Okay, because FB is not perfectly vertical, so it's going to translate some horizontal load that needs to be taken out. But more importantly, because neither GFE or EDC are 2/4 members, is the easiest correct solution. All the ones you've said are also right, but the biggest thing to realize here is this is not a joint between two 2/4 members, right? And so we know, okay, then I have to put EY and EX. All right, so number of unknowns here. Enough. 1, 2, 3 unknowns, and I can write out 3 equations of equilibrium for this, right? So let's do that. Let's do the equations of equilibrium right here. So in the x direction, it looks like I'll have FFB cosine of 71.6 plus E sub x equals 0. And in the y direction, I'll have negative 1226 minus FFB sine 71.6 plus EY equals 0. 3 unknowns, 2 equations, got to go for the moment. Where do you guys want to sum the moment about? Okay, you want to say E because it has 2 values in it. I say F. So I don't have to break it into components and use trig, right? So I'm going to say sum of the moments about F. Okay. Looks like we'll have 1226 times 1 meter, right? Because if we go back up to here, 1 meter from F to the 1226. Plus EY times 2 meters equals 0. So that tells us EY is 1226 divided by 2, 613, and it has to be negative. Which makes sense, because if you sum the moments about F, you don't want this thing spinning, right? If EY was positive, it would be. Okay, so we get negative 613 newtons for EY. I can substitute that back into the equation above. Negative 613 and 1226. So we'll have, where's my negative sign on this here? Doohickey. There it is. 613 negative minus, oh my, 1226 negative plus 613 negative 1839. Oh man, this is where the iPhone calculator really starts to suck. Can someone tell me what 1839 divided by sine 71.6 is? Okay, so it looks like FFB is 1938. And would that be positive or negative? I think that's negative, isn't it? I'm pretty sure since we drew it down, it's actually going to give us a negative value, right? Because I have negative 1226 minus 613 is negative 1839. And then I take that to the other side, and negative FFB sine 71.6 is equal to 1839, so it has to be negative, yeah. Okay. And then we can use that to solve for EX. Anybody get EX for me? What's that? 612? Okay, positive or negative? Positive, right? And that makes sense because if FFB is negative, that means it's going that way. So we need EX to counteract that. Okay? Let's go back. What are we looking for? Why did we start this problem? We're looking for the load in BD, right? We started by saying, okay, well, we know ABC. Can we figure out what it is by drawing a free body diagram there? And even though we were smart enough to figure out, look, I know the direction of FFB and FBD. There's still 4 unknowns. And then we said, okay, so let's look at the other one where we know some information, GFE. We solved that and found FFB. So now we can come back to this one and solve. Right? So I can take my FFB as negative 1938 and substitute that in here, equals negative 1938, okay, and write my equations of equilibrium. Okay, so I'll pause it, and I want you to do that. Write the equations of equilibrium for ABC. So 3 equations of equilibrium, right? Some of the forces in the x, some of the forces in the y, some of the moments about a point. What point are you guys choosing for some of your moments about? B. Good choice, right? Eliminates all the ugly trig. Okay?
You can just do it around C and then you don't have to give you the forces in the X and Y, because if you do
Sure. So Brendan makes a good point. What if I just sum my moments about C, and then I don't have to do some of the forces in the X and the Y, which is clever because we know FFB, so then the only thing that would be an unknown in some of the moments about C is FBD. True. Okay. That's not how I chose to do it, but definitely true. Okay, so here are my equations. You have to be really careful. So we've drawn FB is going as if it's in tension, right? That it's pulling on B, but we found out here that we got a negative value for it. So I have to make sure that I put that negative back in here. And then I do my calculations saying, oh, FFB is going that direction. So I can say FFB in the X direction would be negative FFB cosine 71.9. So is my equation correct? It should be a double negative there. It should be minus a minus, right? Because what I'm doing here is, imagine that I just leave it symbolic, FFB, it'd be negative FB, negative FFB cosine 71.6, right, in the X direction. If I'm saying that way is positive, FFB is drawing going in the negative direction. But then I found it also has a negative value. So it'd be negative FFB cosine 71.6, but FFB is also negative. So it's negative, negative, and it's going to turn to a positive. Okay? Let's make sure I did that correctly in the sign then. In the Y direction. In the Y direction, I would have 1226 going up, some component of FFB going up, sine 71.6, but I know that it's a negative value, so I just stick in the negative. So this one is correct. Okay? And then I sum my moments about B, so I eliminated the trig, and I find that CY is 2452, and then my iPhone calculator failed me, and I'm counting on my students to not fail me and tell me what CX and FFBD are. What'd you get? Negative 2600 newtons. So that would be 2600 newtons in compression. Which do we think it should be in compression? Whew, that's a hard one for me to see. I don't really know. Anybody else get FFBD or FBD? Liana? Sophie, did you get FBD? And did you get 2600? Positive or negative? Okay, negative in compression. All right. So CY method of sections was important, right? You have to be able to get these internal forces. We're going to go well, let's look through a couple more of these. We don't have time to do another example. I'm going to, here, actually, while I have this up, here's 4 homework problems that I would suggest. I don't know what the syllabus says, but here's 4 that I would suggest just from this section. They're all in Chapter 6, 83, 87, 89, and 91. Okay? 83, 87, 89, and 91. Okay? Let's look at a couple of these. Okay? So the first part of the chapter problems are all frames. Okay? So here, if we looked at this, determine the horizontal and vertical components of the force that pins A and B exert on the frame. So if I drew a free body diagram of this, of just the external loads, what would the problem here be? I'd have AX, AY, and BX, BY. That's 4 unknowns. There's a way around that. You have the distributed load, yeah. What do we know about AC? It's a two-force member, right? It looks funky, but it only has loads applied at C and at A. So what's the direction of the force at C? It's along the line that goes from A to C, right? So we could actually solve this by just drawing a free body diagram of CB and putting that unknown C value going up and to the right, and then Bx, By. Okay. How about 72 here? Can we do that on this one? No, there's a load, so both of these are three-force members. So if I draw the free body diagram of this, I'm going to have AY, AX, BY, BX. I can't solve, so what do I need to do? Split it at C, right? Actually, let's do this. I'll make you stay late. Let's do 672. Yes, so you're right, so the question is there lots of equations of equilibriums in dynamics and strengths? The answer is yes. In dynamics, though, it's not equilibrium, so it's, instead of the sum of the forces equaling 0, it's the sum of the forces equals mass times acceleration, okay? So 672 looked like this.
When do we start using calculus instead?
Yeah, you barely use calculus. We'll use it actually coming up here, but right. But remember, as engineers with distributed loads, we squint and say they're rectangles or triangles, and then we don't have to use calculus. Okay? So here's one. We want to find the reactions at A and B. Okay? And we see right off that neither of these are two-force members, so that means that we're going to have AY, AX, and BY, BX. Okay, so there's four unknowns. So if we get to a spot where there's four unknowns and we can't do anything about it, what we need to do is split this guy into two pieces. So one piece will be this guy here. And I'll continue with my AY, AX, and then at C, I'm going to do the same thing. It's going to have CY, CX, right? Looks like I haven't helped myself. I still have four unknowns. How many equations could I write? 3. Okay, so then let's move to the other piece. BY, BX. And how should I draw CY, CX? Same way as I drew them in the other one? Do I want to make them positive CY, positive CX? No, I need to draw them opposite to this. CY, CX. How many equations can I write for this guy? 3. And I can write 3 for this. How many unknowns do I have total? 6. How many equations do I have total? 6. So I can simultaneously solve 6 equations to solve this problem. Right? So let's write them out. Okay? 200 Newton meters. Ah, snap. We'd have to figure out how long that is. I'm going to call this F. Okay? So my equations of equilibrium here would be sum of the forces in the x equals 0. All right, so what's happening in the x? Well, I've got ax plus cx plus f. I think that's going to be cosine 30 equals 0. Sum of the forces in the y, I'll have ay plus cy minus f sine 30. Okay, and then I can sum my moments about a point. I don't know. Let's choose A. Right? And I could write that equation. Then we're out of time, so I'm going to come over here. Sum of the forces in the x equals 0. Well, it looks like I have negative 800 negative cx plus bx equals 0. Sum of the forces in the y equals 0. Let's see, I'll have by minus cy. And then sum the moments, I'm going to sum them about b. I'll have cy times 2 plus cx times 2 plus 800 times 2 equals 0. Okay. Now, some of the moments about A is kind of funky. There's some trig you're going to have to do to figure out, okay, the components of F, or you could figure out what this perpendicular distance is. Either way, there's some trig, but you can sum the moments of this about A. And you can see I have 6 equations. You have to solve all 6 simultaneously to get your answer. This is where you want to use your calculator, right? It's a bunch of punching in the numbers. They're not complicated equations, but they have lots and lots of pieces. All right? Okay, please do those homework problems. I'll take questions on them on Wednesday. But I'm done covering this, and we're moving on to Chapter 7. Right? So unless you ask me questions, you're not getting any more content about this. So you need to probably do some homework in between now and Wednesday.
So just in cases like these where you split it up and you still have too many unknowns, you have to solve all of these.
Yep. So the question is, when you look at this and there's too many unknowns, and then you split it up and there's still too many unknowns, you have to solve them simultaneously, right? Because there's 4 unknowns here, 4 unknowns here. That's indeed correct. But there's only 6 unknowns total, and there's 6 equations total, so you can solve it.
Wait, so if you're to plug it into your calculator,
Mm-hmm.
plug in all of it?
Yeah, you plug in all 6 equations at one time.
So they have to be equally true.
Yep. Okay? Highly recommend practicing that.